Okay, so last time we just discussed the two numeric systems. One is the binary system, and the other one is the decimal system. And at the very end, we also introduced the hex decimal. So technically, we actually covered three different systems. So decimal, and the binary, and the hex decimal. Okay. Now, decimal is the system we use in our life. So it's also called the base 10 system. And the binary is the base 2 system. Now, hex decimal is widely used in engineering. So basically, it's called the base 16 system, which is used to represent any numbers, using base 16. Typically, people use the hexadecimal as the shorthanded notation for the binary, because the binary system it's kind of good. You can represent any numbers using binary and notation. However, the binary notation seems only allowed to use two symbols, so it tends to be very long. So even if a small number, you're going to take a lot of digitals. You need to write a very long sequence of digitals, so binary digitals, to represent a number, even if it's a small number. So that's why hexadecimal is introduced. So you can actually easily, convert the binary into hexadecimal, and which takes a very small space. Okay, so today we're gonna continue to talk about the binary system and we're also gonna talk about how the computer system represent different data using the binary system. So we're basically gonna cover the first one is a textual representation. Okay, how does a computer system represent any text message and any kind of like a document that's written in English language or in French or in any other kind of language? So it's a textual representation. And then we're going to talk about how to represent numeric values, numbers, like a number like 20, 25, or even like a floating point numbers. Okay, how can I represent a number? And then we can talk about how can you represent some kind of multimedia type of data, like a sound, images, also like a video. We are not going to talk about a video, but basically, video is just just an image. So instead of actually using a single image, video basically consists of a whole bunch of images they put together. So video is basically the image. So so in module 4, we say that any data can be stored in computer memory as a binary digital. Remember that all the computer components are made by a device that represent either actually 0 or 1. It's So the computer system, basically, for any computer system, there's a binary in its DNA. So every actually device, like processors, memories, they all actually build some kind of device that deal with the binary. Remember that the transistors, the gates. So most of the complicated actually circuit, digital circuits are built by millions of gates. Each gate gonna actually process, binary digitals. So the computer device basically processes binary digitals, store binary digitals. So that's why we have to learn how to represent different data using the binary digitals. Okay. So even though data are often viewed as the lowest level of abstraction from which information and knowledge are derived, so we use data and information interchangeably in our study. So basically, if you actually take any courses like information technology, you know that data normally represent the raw data. Okay, so and the information basically is actually built from data, but it's actually people basically encoded this data into give this data some kind of meaning. So data and information are slightly different, but most of the time people use these two terms interchangeably. So also in this case, in this class, we don't differentiate that data and information too much. So just realize this. Technically, they're not the same, but we're going to use these two terms interchangeably. So with modern technologies, text, numbers, pictures, audios, and pretty much nearly any other form of information can be ultimately converted into a string of bits. Remember the bit. Bit basically represent either 1 or 0, right? So if you talk about a string of bits, you're talking about a sequence of binary numbers. A sequence that only contains 0 and 1. So then the computer actually store these binary digitals in the computer memory, and the computer processor basically process the sequence of binary bits. Now, first thing we're going to talk about is a textual representation. Now, how does a computer system store and process text documents? So typically, a text document is decomposed into individual characters, such as alphabets, numbers, and other symbols. Now, if you want to actually see the complete list of these text documents, you can basically check the keyboard. A keyboard contains the alphabet from A to Z, lowercase, uppercase, the capitals, and also the numbers 0 to 9, and the other symbols like factorial, pound sign, dollar signs. You have a whole bunch of different symbols, and these actually put together and create a text document. So the text document is something we actually see, but if we want to store the text document into the computer system, somehow we have to convert this text document into a binary sequence. And this process is called encoding. Okay. So the computer memory only stores binary digitals. So in order to store the text document, we first need to identify a list of all distinct characters. And we call them character set, and use in the document. And then represent each of the character with binary digital code equivalent. Okay. So let's see. So in typically, what kind of characters we want to represent. What character set do we need to represent? Okay, so we have 26 letters. Okay, so from A to Z, 26. And also we want to represent A to Z, capital A to capital Z, another 26. So that's total actually 52, right? And also we want to represent 10 numeric digitals from 0 to 9. Okay, this basically add additional 10 characters. So it's a 52 plus 10, that's 62. And also all the other symbols such as punctuation characters or even space characters. So some of the examples are pound sign, Factorial, and pound sign, and there's a whole bunch of even like a comma, dot, and the parentheses, and the left and the right. So you have so many different symbols that you want to represent, or even a space. Okay, so when you press the space bar, on a keyboard, when you press the space bar, even you actually don't print anything, but you actually create a space. Now, space can also be, interpreted as a character. So in the computer system, so when you store a space in the computer system, you need to store as a character. So don't think a space is nothing. There's something there. Okay. So these are basically the character set we want to represent using the computer system. Okay. Now, how you can represent each of these characters? Or on another word, how can we encode these text, texture actually, all these characters. So there are many standards. A well-known character set is called Ascii Code. Okay, so this is actually a very early character set. It's called Ascii Code, which basically stands for American Standard Code for Information Interchange. So initially, the Ascii Code basically was to define the character set used on the computer keyboard. So if you count the number of characters on the keyboard, you will find out there are many of them, but they are fewer than 127, 128. So this is actually initially defined in 1963 and finalized in 1968. Okay. So basically, Ascii code represented characters as 7 bits. Okay. So that means for each character, you can store the character using a sequence of 7 bits. Okay. Now, for 7 bits, let's say, for example, you can represent one of the character using 7 bits, say 0, 1, 0, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7. Okay. Now, you can use this to represent a symbol. I don't know what it is, but it's defined. Okay. Now, if you want to find out what does this 7 bits represent, then you can actually check the Ascii code. Okay, it's called Ascii table. Okay, so we can find out later. Okay, so basically, so you can use 7 bits to represent a character in the Ascii, in the Ascii code. So now the question is, with 7 bits, how many characters we can represent with 7 bits? Let's do a small math.
2 to the 7th.
2 to the 7th. So it's pretty simple, right? You have 1 bit, 2, 3, 4, 5, 6, 7. Okay, so for each position, you can either put the 1 or 0, okay? Or 0 or 1. So there are two actually choices. And this here, we can put the 1 or 0. There's another 2. So for each position, you can put you have 2 actually different choices. Okay. So with the combination of these, numbers, we can put all these multiply under 2 to the 7, which gives you 128. So basically, with 7 bits, we can represent total of 128 different characters. So that's basically what the ASCII code can represent, 128. Okay. So now, the standard ASCII code, which used 7 bits, was later extended to an 8-bit pattern called Latin-1. Okay. Now, for various different reasons. Now, first one, 7 bits. 7 bits actually is kind of sequence that it's kind of weird sequence because now when we use binary, we tend to actually represent number which is actually an even number. Okay, so 7 bits it's kind of weird number. So that's why people want to extend the 7-bit to 8 bits. Okay. Now the other reason for this is because in a computer memory, the computer memory is basically built upon a whole bunch, built upon the cells. We call the cells. Okay. So the computer memory is built upon a small unit called the cells. Okay. So each cell contains 8 bits. 8 bits. Now 8 bits is actually a favorite number. Everybody likes this number because so that's why they use a dedicated term called 8-bit. They call 8-bit a 1 byte. Okay. Now, not only 8-bit is a even number, also it's actually the power of 2, so which is 2 to the 3. So it's actually a very good number. So with 8 bits as a cell, so that means the computer memory consists of a whole bunch of cells. Each cell is 8 bits. So now, if you want to store a data, okay, like a character, like a texture messages. Now each character should be stored. If you store each character as 7 bits, that's kind of weird, right? Because if you have like a computer memory like this, so you have a computer memory. So I have a 1 cell, 2 cell. So it's kind of a sequence of cells. Okay. Each cell has 8 bits. Now, each cell also has an address. Okay. Now the first one in the sequence is called address 0, address 1, 2, 3, 4, 5, and then 6, and then you can just continue. Okay. When you store a data, so if you store a data in the computer memory, you're going to store into the cells. Now, if you have a 7 bits, then you can store a 7 bits in the 8 bits cell, right? In 8-bit cell. However, you have one more free cell, free bit. Okay. So now what do? If you store another 7-bit characters, then you can actually store 1 bit in here, and you can store the next 6 bit in the second cell, right? So 1 bit here, 6 bit here. So then you have that leaves you 2 bits here. Now, if you store next character, you're going to take another 7 bits. So you're going to store 2 here and 5 here. So this is not really nice now, because when you actually try to pull the data off the computer memory, it's so difficult to remember which character is stored in which cell or which, because some of the character actually stored, part of the character stored in one cell, part of the character stored in another cell, you know. So this can actually cause a lot of trouble. Also, when you access the memory space, sometimes it can actually, the performance is going to suffer, because you have to actually first remember this particular character is actually split into 2 parts. One part is in one cell, the other part is in another cell, and you know, it's not really convenient. So that's the other reason why people finally extend the 7 bits into 8 bits, because with 8 bits you can store each character in one cell. The next character you store in another cell. Oh, okay. So let me tell you this: even before we actually extend the ASCII to 8 bits to Latin-1, people actually also store each character in one cell, and they're going to waste one of the bit. So they prefer to waste one of the bit, because they want to store each character in one cell. So the 1 bit is still going to be wasted. Okay. So once actually they extended to the Latin-1, so then you can actually use 8 bits. With 8 bits, you can actually double the character set, right? The character set used to be like a 128 with 7 bits, but now with 8 bits, you can double this number to 256. So with 256, you can represent more symbols. Okay, so you can represent even like a non-English letters and some of the mathematical symbols. So you can actually represent more things. Okay, and without causing much of the storage problem, because now you're going to take the whole cell for each character. Okay. Now, next one basically gave us some kind of idea what the ASCII code looks like. Okay, so I don't know whether you can see this table correctly. Can you see it clearly?
Yes. Yes.
Okay.
Pretty good.
Okay, I hope you can see this clearly. And so with the this ASCII ASCII conversion chart or ASCII table, so you can see that here this column represents the binary, and this is actually the corresponding decimal value. Okay, so now we can see that each binary sequence represent some kind of characters. Okay, so all 0 basically means now I don't even know what is SHO, but so let's see actually some of the things we know very well. So for example, like a Factorial, then you can use this to represent Factorial. It's a 001, 00001, which is 33. Okay, with a decimal number, it's a 33. Okay. Now, what is actually the numeric numbers from 0 to 9? So it's actually from 48 to 57. That's the binary representation. Okay. Then you have a colon, semicolon, less than, equal, greater than, question mark, and then we start to see the alphabet. Okay, so from A all the way to Z. Now these are all capital, alphabet. So A is actually decimal number 65, which is this, and the Z is 90. So it's just basically it's just an increase by one, So from 65 to 90, that's total of 26 characters. And where is the alphabet, the lowercase alphabet? A to Z. Yeah. So it's a 97 to 122. Okay. Now let's just check what this number. It's a 01 00111. Let's see what it is.
Excuse me, Professor.
Yes.
One of the colleague is not able to log in the session. She's trying since long time. It says that we should allow her in meeting.
Okay. I don't see anything here. Oh, here. Sorry, I did not see the pop-up window.
Thank you.
So are you in now? Okay. So let's see. What is this number? The number we just talked about. Let's see. 01001111. Okay. So that's the ASCII code with 7 bits. So what in the extended actual ASCII code, you just need to add another 0 here, right? So what is this? So it's actually 001. Okay. A single quote. It looks like it's a single quote. Okay. So that's basically the ASCII code that represents a single quote. So this is how the computer system actually store the textual messages. For each actual character, characters, they basically just store as the ASCII code. Now let's see some of the example. We always use the extended ASCII code, okay, using that table. Okay. So with the extended ASCII code from table 3.2, well, I don't know. I don't see. I assume that's a table 3.2. We can encode and store 6 characters string like a hello as a bit pattern. Okay. Now, one thing I have to mention is that so extended ASCII code is backward compatible. It's backward compatible. Okay. Backward compatible. So basically, it means that the value for the extended, if a character is actually can be represented using the 7 bits ASCII code, okay, so then the extended ASCII code basically has the same value. So that means if you say 7 bits ASCII code like a 011101, then the extended ASCII code is just add a 0. So it's basically the same. So when you actually, if if the most significant bit is 0, then in that case you can get rid of the 0 and still actually represent the same thing in the 7-bit ASCII code. So it's backward compatible. Now let's actually take a look at this. So how can I represent and store in a computer system the message hello and the factorial? So with the ASCII code, you can check what is the ASCII code for H, capital H, right? And what's the ASCII code for E? And what's the ASCII code for L? L. So these are the same. And the O and the factorial, right? So you can actually easily check the ASCII table. Let's see, 0, 1, 0, 0, 1, 0, 0. Let's see. What is H? H. Okay. So it's a 0, 1, 0, 0, 1, 0, 0, 0. So that's capital H. So you can easily, do this by checking the ASCII code. So now, here's the thing. If I ask you to, to encode a character into the ASCII code, or doing, vice versa, then you don't have to remember which character represented by which ASCII code. So all I want you to know is that as far as you can, look at the ASCII table and find, doing this conversion, that's okay. Okay, you don't have to remember the number. Okay. This table is very difficult to remember. Some people actually remember the alphabet. For example, like capital A to capital Z, that's like a 60. I think it's a 65. Okay. And also lowercase is 97. So if you actually remember what is the number represent the character A, then it's relatively easy to figure out what is the number for the other character, because depend on the relative location of the character to the A, then you can just add the corresponding number and you can get the corresponding ASCII code. So, but you don't have to remember this. Okay. Now ASCII code was defined in 1960s. Now, as computer becomes more and more popular, now, so people just have some kind of, there's a high demand that people want to extend these ASCII code. Even like extended ASCII code, it's still a very small character set. Okay, so they want to extend the character set. Okay, because people actually coming from different world. Some people actually speak English, but there are more people speak different languages. Now, in the ASCII code, you only have an alphabet, and even in the extended ASCII code, you have some kind of characters for the actually in like in a Western country like German, French, but there are still actually a lot of languages that you cannot represent using either the ASCII code or extended ASCII code. So that's why Unicode is defined. Okay, Unicode was defined by one of the organizations in the United Nations. So they try to define a certain kind of standard because they don't want actually people to actually encode. So for example, like a Japanese, Russian, Chinese, for each of the character, they want to actually create some kind of a standard. So for each Chinese character, they're going to use the same code, binary code to represent it. Okay. Now certainly 8 bits is not enough. So you need to extend the number of bits. So Unicode is actually, it's rapidly gaining popularity as traditional ASCII code can represent. So the Unicode basically use, instead of 8 bits for the ASCII code, the Unicode use 16 bits. The Unicode use 16 bits. Now, what does that mean? Now, with 8 bits, you can represent 2 to the 8 different characters. Now, 16 bits basically means 2 to the 16. Okay. That's a big increase, right? Can you imagine? Can you imagine that? So if you actually just increase 1 bit, you actually double the characters. Okay. You double the characters you can represent. Now you actually increased by 2 to the 8 times. Okay. So that's a very big character set. Okay. Now, so far, even with 2 to the 16 the Unicode, there are still some of the binary sequence, like a 16-bit binary sequence. They are not defined yet because they could not find enough characters. So with 2 to the 6, you can have total of 2 to the 16 is 65,536 characters, and so far, there are still actually some of the Unicode, the binary sequence of 16 binary sequence, which are not defined yet. Okay, so that's enough to store most of the world's characters. Okay. So Unicode can be implemented by different character encoding, and the most commonly used encoding is called UTF-8, which was designed to be the natural extension of the extended ASCII code. Okay. So that means Unicode actually UTF-8 is backward compatible. Okay. Now, what does that mean? So that means if you want to represent English letter A, okay, or letter H, let's say, capital H. So what is a Unicode? The Unicode is, you just add
80.
80. So that's the Unicode using the UTF-8. Okay, which is pretty good. Okay. So this is basically how we can represent the characters. Okay. So here's another example. So let's see. Example for the following message encoded in 8 bits extended ASCII code. What does it say? Okay. I gave you 4 minutes. Can you encode it? You basically need a ASCII table, right? So I don't know how can I display the ASCII table here. Let's see. Let me do this. I can find the ASCII tables on the website. Okay. The first one is 0101. Now, if you can search the website, you can basically find out. You can find there are a lot of ASCII tables out there. So 0101, 0111. Okay, 010111. Yeah. Okay, I gave you 4 minutes. Can you actually figure out what is this message? Okay. I'll be back.
Professor,
Yes.
we are unable to see the code actually.
Okay. What is that? What are you trying to say? You can type. Any?
She's saying that we cannot see the question.
Oh, you cannot see the question. Okay. Okay. I just want to see both the question and the ASCII code, but ASCII table, but that's not possible. But you can actually you can search for the ASCII table on your local machine, so you can see this. Okay. So that's that completed sequence. Let's see. I'll be back in 3 minutes. Okay, what does it say? First one is W, right? Let's find out it's W. What's the second one?
Knowledge.
H, lowercase h.
Okay, H. Okay, H. Oh, let's see. H. The other one is 110. WHE, right? So this is a sand. Where? Okay. So what is that next one? So it's a 001. Oh, that's space.
Space.
Yeah. It's just a space. So what is next?
Lowercase a, R, E, space,
is where
lowercase y,
Y.
O, U.
Okay. U. That's looks like a question mark, right?
Question mark, yes.
Yeah. Okay. Where are you? So this is actually the message, and this is actually what happens in the computer. This is actually the actual code that is stored in the computer system. Okay. Using the Ascii code. Okay. Now this is actually for the character. Now if we want to actually represent a numeric values, like a number, integer, floating point number, so any numbers, a numeric can be represented and stored in the computer memory as well, because that's the initial purpose for the computer. You know, you want to do arithmetic, you want to do addition, multiplication, just like what we did in a previous module that we can store, you know, as a number. You can do the addition, multiplication. Now with the ASCII characters, we know that the digital 0 to 9 can be represented as an ASCII code, right? So that's why if I actually ask you to store a value 49, okay, 49. Now looks like we have two ways. We have two ways to represent 49, right? The one way we can do it is just the one we used before. We can directly convert the decimal number 49 into the binary number, right? So we can represent 49 with a binary number. Now, another way is just something we just learned today. Because in the ASCII table, you can actually represent digitals using the ASCII code. So then we can find out what is the character 4 if we treat the number 4 as a character. So let's go back. What is 4? Okay. So 4, you can easily find out 4 is this. It's a 00110100. It's a 00110100. And then what is 9? 9 is this. So then you can use 2 8-bit character to represent 4. Another 2, one actually 8-bit to represent 4. Another 8-bit to represent 9. So that's the 49. Okay. Now the other approach is you directly convert 49 into the binary number. Okay. So what is 49? Let's see. The 49 is, you can write 49 as 32 plus 17, right? Yeah, 32 plus 17. And the 17 can be written as 16 plus 1, right? So that's 2 to the 5 plus 2 to the 4. 16 is 2 to the 4. And plus 2 to the 0. Okay. Now, what is the ASCII representation for 49? That's a 1. Oh, sorry. Looks like it's a 1, 0. Because 2 to the 3 is missing, right? 2 square is missing. 2 to the 1 is missing. You basically miss 3 numbers. Okay. So that's 3. 2 to the 3, 2 square, 2 to the 1. We miss actually 3 numbers. So the 2 to the 4 is here. So that's 2 to the 1, 2, 4, 8, 16. So that's 2 to the 4. And 2 to the 5th, that's 1. So 49 is 11001 0001. Okay. Okay. Now, which one is better?
Binary.
That one looks better, right? Now, it's hard to say, because if you treat the 49 as character, if you interpret the 49 as character, not as a number, or not as a number, so you can actually do arithmetic, you can do addition, multiplication, then ASCII code should be okay, you know. If you want to actually treat the 49 as a number, so you can perform the math, like 49 times 2, you can do the addition, multiplication, then you treat, you can directly convert 49 into binary representation. That's probably better. But the other way, you can actually use 49. So in most of the computer language, now, if you represent it using ASCII code, or represent it using the binary number, they're different. You can treat this as a string. So this is just using character. It's just like you can treat like a 4, 9, but enclosed with a double quote. It's kind of a string. You can treat it as a string. Okay. So this way, it's actually a ASCII code. Okay. Now, if you actually use this, it's just to treat it like an integer, right? So you can define, if you want to define int x equals something like int int x equals 49. So then this 49 is treated as an integer. Okay. But if you use the ASCII code, it will be treated as string. Okay. So you cannot do math. Okay. So sometimes it's people actually use the ASCII, using the ASCII code representation, but sometimes you use the binary representation. It depends on how you're going to use these numbers. Okay, but if you treat it as a numeric value, definitely use this. Okay, use the binary representation. So this is actually, we explained this here. So the problem with ASCII character is that it is very difficult to perform mathematical or Boolean operations. numbers stored as ASCII characters. So it's generally regarded as inefficient to store number using ASCII characters. Okay. Unless you really want to store number as characters. For example, the other example is like a street number. Okay. So if you want to say you want to actually write people's address. So the whole address is just like a message, like a 160, 160 Pearl Street, Fitchburg. You know, that's Fitchburg, the address of Fitchburg State University. So then, in this case, 160 is treated as character. So you don't want to do math with it. So you can store the street number as ASCII code. So that's okay. So honestly, it's less efficient because for 49, if you use the binary representation, you just need 5 bits or 6 bits. But here, each character going to use 8 bits. So 2 digital going to use a total of 16 bits. That's just for extended ASCII. But if you use Unicode, now the 4 going to be actually 0000. You have 80 before it, right? And the second one, you have a 0000 before these sequence. So you're going to use total of 32 bits. Okay. If you use Unicode. Okay. So that's why typically if you want to represent a numeric values, numbers, then you can use binary notation. So with binary notation, now for 16 bits, you can represent from 0 to 65,535. That's a very big range of numbers. Okay. Now, if you use ASCII code, 16 bits only allows you to represent 2 digitals. Okay, right? But here you can represent up to 5 digitals, which is actually, you can represent a large range, large actually values. Okay. So therefore, numeric values are typically stored as binary representation or tooth complement notation if you want to do a math. So remember, we talk about tooth complement, right? So if you have 16 bits, you can use a tooth complement system with 16 bits. Okay. Next. Okay. How can we represent a voice, a sound? Because for most of the modern computer systems, you want to represent, you want to store some kind of music. You want to store someone's voice or some actually your favorite song, something like this, right? So before we do this, we need to figure out how the sound is going to be stored in the computer system and what the sound is represented in, you know. So sound is actually a series of compression waves. So generated by mechanical vibration. Okay. So if you have a string, you actually, you know, play with a string. The string gonna vibrate. They're gonna make a sound. When you actually speak, you basically your tone actually inside it just vibrates. So basically generate a sound. Okay. Your speaker is also, you know, it's sometimes you use a paper, just vibrate that generate a sound. Okay. So a sound typically can be recorded as an analog signal. Okay. So there are two actually you can characteristics. You can characterize the sound by 2 things. One is the frequency of the sound. The other one is called intensity. Okay. The frequency of the sound actually contributes to its pitch. Okay. And it's the rate of vibration. So, for example, if you have a string, and you actually you basically play with the string gonna vibrate. Okay, so depend on how tense the string gonna be. Sometimes the string gonna vibrate at a very high speed, very high frequency, and the voice gonna be very how can I, when the vibrator is actually very slow, you're probably gonna see when the vibrator is very fast, you're gonna see when vibrator is when the change is very slow, going up and down, you're gonna see gong, gong, gong. But when the vibrator actually rate of vibrations increase, you're gonna see gong, 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 and the rate is increased, keep increasing. You're gonna see gong. So eventually, you're gonna see a very actually steady sound. Okay. Now, typically, a women's voice is actually has a higher frequency than a man. So now the intensity is actually it's basically measure the loudness. Okay. In many times we call the amplitude. Okay. So the sound actually is basically stored as a sound as a waveform. Okay. So so for example, so you have here you actually measure the amplitude. So here's the time. So you can actually, sound that can actually looks like this. It's a louder here, relatively, lower voice, and louder again, louder again. Okay, so you just can actually move as a waveform. Okay. Now, this is actually how the sound is recorded. It's recorded as a waveform. If you actually use the scope, any kind of device, if you're an engineering student, use a scope, you can basically measure the waveform for the sound. Okay. Now, the analog is actually a continuous function. It's continuous. Okay. Now, how can you store an analog waveform into the computer system? Now, remember, computer system only store binary digitals. So the binary digital is not continuous. It's actually a discrete. You only store either as 0 or 1, 1 or 0. There's no actually, you cannot continuously store a waveform using the digitals. So that's why we need to go through a process called analog to digital conversion. Okay. Now, how can we do this? Let's actually take a look at the next slide. And I will back because eventually, once you convert analog, the sound wave to a digital wave, digital representation, then sooner or later, when you actually try to hear the sound again, you have to actually convert the digital back to the analog. Okay, so let's take a look at this. So here's an original sound wave. Here's amplitude. Okay, so the amplitude you can actually measure in terms of loudness. You can use a number, right? Yes, for example, here's a 100. Here's a 50. Okay, 25, 75. So this sound wave, this is the amplitude. So this is the loudest within this time period. So this is 0, and this is time. It can be measured as second or millisecond. So whatever, So this is basically the music. Just as the time goes by, it just continues. Okay. Now, how can you digitalize the sound wave? So this is how the computer system is going to do. So typically, the time going to measure as based on, for example, like a second. So let's say here's 1 second. From here to here, it's 1 second, and 2 seconds, 3 seconds, 4 seconds. So this is actually a music of 4 seconds. Okay. Now, in order to, convert the analog waveform into a digital, then you need to actually pick a some of the samples. For example, so when I say, oh, okay, so you have 4 seconds. So I can pick actually, let's say, I pick a sample here at the 1/4 of the time, and the 1/2 of the second, and the 3/4 of the second. So I pick a sample here. So I can actually, I pick a sample over here, 0. 0 actually, there's no voice, right? It's silent. So then the voice starts to go up. At the 1/2, the value is, I don't know what it is. I say it's 30. Okay. Okay. And now in 1/2, it reaches 50. And the 1/3/4 reaches 75. And at the 1 second, it reaches, let's say, 85. Okay. So I pick, for every 1/4 of the second, I pick a sample. So I pick another sample here. I pick another sample here. Okay. Make sure that each of the time interval is just 1/4 of a second. Okay. It's always 1/4 of a second. So I pick a sample here, 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 right? So I can record the amplitude at each of the time. That's the amplitude, okay? So now, so basically the frequency is not really high. So only actually every second, for each second, 1 second, I only pick actually 4 samples. Let's see, how many samples? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then additional one. So I only pick up these samples. Okay. So every 1/4 of a second, I pick up a sample. Okay. So then what I do? So instead of do this, I can actually record the sequence of the numbers. Okay. So the sequence of number becomes the amplitude is 0 at the time 0, right? The amplitude is 30 at the time 1/4 of a second. In 1/2 a second, the amplitude is 50, right? And here, the amplitude is 75. And here, amplitude is 85. And here, the amplitude is, 85. Here, it's 100. Then amplitude is 85 again. 85 again. So the next one is, looks like 80. Next one is, 73. This one is 50. What is this? 40. This is the lowest, 30. 30. Increase. 33, 50, 35, and then 50, 55, 60. Okay. So 50, 30, 30, 35, 50, 55, 60. Okay. So now I just record this waveform. I just record it as sequence of numbers, right? Now each number basically represent the amplitude for every 1/4 of a second. Okay, so then I record it as this. Now that's called sampling. Okay. Now here I use slightly different than it's called a sampling. Okay. Now this is how I sample. This looks like I actually put more samples than this. Right here I only take 1, 2, 3, 4, 5, 6, 7, 8. 8 sample. But here I take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. It's 17. Here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I pick a 9 sample, but here I pick actually 17 samples. Okay. Now this is called a sampling. Now, how does the computer store these values? Okay. Now let's first do it. Once you store this sample, okay. So once you pick the sample here, like it's a, I use different amplitude. Okay. Here I use 100. Okay. So if I use this sampling, then what I do is I store these sampled value, the amplitude, the sampled value, sequence of amplitude into the computer system. Okay, into a file. We call this file some kind of voice, like an MP3 or whatever. It's called different format. Okay, so I store this value and then send out in the internet. Now, when the receiving side receiving this sample, and if they want to recover, they want to restore this sound wave. How should they do it? They just need to rebut this based on these numbers, right? So here they're going to do this. Next one, next one, next one. So they can actually rebut these one. But instead of its continuous waveform, it's not a continuous. It's discrete. Okay. Any questions on this? Now take a look at this example. So once you actually store the sound wave, you can store, in this case, looks like if you have a 4 seconds, 1, 2, 3, 4, and then you only pick actually samples here, and every half a second that you pick a sample. And the sample going to be 0, 6, 9, 10, 8, 6, 5, 6, 8. That's the sample you actually store. And that's a sample, if you want to actually recover it, okay, if you want to read, when you store this, that's called digital sound. So you can store as a file, and you can send the digital file to your friend through like an email, FTP. You can as attachment. So say, here's my voice, and actually the voice actually stored as a sample. Okay. Now here I use decimal, but when you actually store the number, you actually use the binary, right? You use the binary to store it. Okay. So once you store this number, and then once you want to restore the sound wave, what are you going to do? Okay. Here's what you have. 0, 6, 9, 10, 8, 6, 5, 6, 3. Now, basically, you lose the information between 0 and you here and 1/2. Here's 1 second. So you basically lose the information in between, right? And you lose the information in between. Now, how can you rebuild? So basically, you just draw the line here. Draw the straight line. So this is actually the digital sound wave. This digital sound wave basically represents the original sound wave. Okay, that's called digitalize. Now, what's the problem? What's the problem here? Does the digital sound wave truly represent the original sound wave? Does the digital sound wave truly represent the original sound wave? Yes or no?
No.
The answer is no, right? It's close, but it's not the same. So the digital wave is just actually, approximately represent the original sound wave, but not the same, okay? Because digital sound is actually, you just actually lose a lot of information in between. However, it's close. Now the question is, now if I use the analog to digital conversion, if you actually try to digitalize this, now how can I make the digitalize the voice close enough to the original one? How can I make the digital sound close to the original sound?
Increase sample rate.
Yes, you increase the sample. So here, it's obvious that the digital sound is just approximation for the original sound wave. So now the question is, how accurate can digital sound be? And how can we improve the accuracy of the digital sound? Okay. You just need to increase the sampling. Okay. Now, even if you increase the samples, like instead of actually pick 2 samples in a second, you pick 4 samples. So you double the number of samples. Or 4 samples is still not enough. You pick 8 samples, or 16 samples, or 32 samples. So you just increase the number of samples, right? So if you actually feel it's not calculated, you increase the number of samples, okay? But it's still not continuous, because so between every 2 samples, between the samples, you still lose the actual amplitude. So you actually just use an estimate. It's just basically draw the straight line between these two. You draw the straight line. You draw the straight line, right? Now, however, you will find out the digitalized sound wave is much, much closer to the original sound wave. Okay. Now, however, if you actually keep increasing the sampling, keep increasing the samplings, then sooner or later, we hope that the digital sound, even though it's not the same as original sound wave, but it's so close to the original sound wave that our human ears cannot hear the differences. Okay. If that happens, then that's good enough. Because then, so you keep increase the sampling, that you create the digital sound, and then you can actually use the binary, use the numbers to store these digital sound. So then you can store as a file, and you can actually transfer this file to the remote side, so the other side can play that music, right? But they don't play the original sound wave. They play the digitalized sound wave. But that digitalized sound wave is so close to the original one, so people cannot tell the difference. Okay, so that's basically the idea of digital sound. Okay, so when you recreate, so if you have more samples, then you can actually restore the sound, so you can actually restore the sound as close to, so close to the original sound that you cannot actually hear the difference. Okay. Now, so the number of samples per second is known as sampling rate. Okay. So theoretically, we can make the sampled sound wave as close to the original one as possible by increasing the sampling rate until our ears can no longer tell the difference between them. Okay. Now that's enough. You don't have to continue, because if you cannot hear the difference, then why you want to keep increasing the sample? Because when you increase the sample, you actually increase the sampling rate. You can actually increase the size of the file because you're going to increase the numbers, right? So that's a trade-off. You can keep increasing number, but when you actually increase the sampling rate, you can actually list it, for the same amount of music, you can actually dramatically increase the size of the file to store the sound. Okay. Now let's see actually some of the examples. Okay. The other one. So now let's go back to the question like this. Okay. Now suppose we actually use the digital sound. Okay. We have 0, 6, 9, 10, 8, 6, 5, 6, 8. Okay. So now we can install these digital sound, right? Okay. So that's a digital sampling, the digital sound. Okay. So we want to install as a binary. Okay, binary digitals. Okay. So now, how many binary bits do we need to store each of the amplitude? Now, in this particular case,
4 bits.
I think 4 bits should be enough, right? For this particular section of the sound wave. So then the first one going to be 0, 0, 0. Second one going to be 0, 1, 1, 0, right? The third one is going to be 1, 0, 0, 1. That's 9. 10, 1, 0, 1, 0. 8. That's 1, 0, 0, 0. 6, 0, 1, 0, 1. 5, 0, 1, 0, 1. 6, 0, 1, 1, 0. And 8, 1, 0, 0, 0. Okay. Yeah. So we can actually store this information over here. Okay. Now, clearly, in this case, 4 bits should be enough. Now, what about if we have a sound wave like this? Let's say this is 25. Okay, now we still try to use 4 bits to represent this digital sound wave. Okay, now this is okay. Now this one, I think this is more than, this is 10, right? This is almost like 20. So you basically have a sound wave like a 0. Well, that's 8. So 0, 8, 20, 25. 25, the next one is also 20. What's the next one? This is like 9. This is 5, okay. And this is actually 5. This is 8. Okay. So now suddenly we have a very loud extra voice over here. Now, if I still use 4 bits, what the sequence of the sound is going to look like? 0, 0, 0, 0. 8 is okay. 1, 0, 0, 0. What is 20? With 4 bits. The highest number we can represent is 15, right?
Yes.
Okay. So if it's 20, okay, I cannot represent 20, but that's the highest number I can represent. And with 25, and here it is. Here it is. And 9, that's 1001. Okay. And the rest of the numbers okay. So I can actually use 4 bits. Okay. That's a limitation of the digital sound. Now, to actually, if you don't want to lose any sound information, then you can increase the number of bits, right? So how many bits do I need? For 25, you need I think 5 bits should be enough. Like 5 bits, you can represent 32, right?
Yes.
Yeah, you can use 5 bits. Now, so you can use 5 bits. So everything actually you can use 5 bits. Okay, then you can actually complete. So you can actually do this by increase the bits. But however, if you increase 1 bit for each amplitude, then you're gonna increase the size by 1/5, right? So you're gonna increase like a 20% of the size. So that's unfortunate. That's the cost that you have to pay. Okay. Now, so this is actually the number of bits you're going to use to represent each amplitude is called bit depth. Okay. So that's the other factor that impacts the quality of the sound. That's called the bit depth. Okay. The bit depth is the number of bits used to encode each sample. Okay. So here, if our bit depth is 4, then for a moderate music, 4 is good enough. But if you have want to play an orchestra, sometimes the voice is so loud, sometimes it's so quiet, and the voice changes actually dramatically change from very loud to very low. Then I think 4 bits going to be not going to be enough, right? So you need more bits. Sometimes even 5 bits is not enough. You actually, if you have suddenly a spike and suddenly a big spike over here, then you need more bits. Okay, so that's basically called bit depth. So now we know to actually create a sample of the sound, you need 2 things. One is the sampling rate. For every second, how many extra samples we're going to pick. The bigger the sampling rate, the better. Okay. Now the other factor is the bit depth. For each sample, okay, when you pick sampling rate for each sample, if you can use like 8 bits, you can use 16 bits. So depend on how many bits you can use for each sample, that's called a bit depth. Now the quality of the sound actually depends on both the sampling rate and the bit depth. on two things. One, the sampling rate. Two, the bit depth. Okay. So now here, if you like this one, even for this one, if we use X 3 bits, bit depth, then the restored, the digital sound are going to look like this. Okay, because with 3 bits, the largest number you can represent is, I'm sorry, it's for 3 bits. The largest number you can represent is 777, right? You cannot. The largest number is 111, so it's a 777. So the largest volume going to be 7, not 8. That's a bigger loss. Okay. Now, the next thing we're going to talk about is the digital audio formats. Okay. Now, the music CD, if you still remember, the day when we played the music with a music CD. Okay. We're not talk about a Sony Walkman that we used actually music tape. Music tape is not digital. Okay. But now we talk about a CD, right? The music CD, it was very popular in 1980s, 1990s, or even actually 2000, year 2000. So music CD was really popular. So you can actually buy a CD and play in a CD player, right? Now, music CD is very, very good quality, It's a high quality sound, okay? Now, what's the sampling rate? So the music CD used the rate of 44,100 samples per second. That's a lot. In a second of music, you actually pick 44,100 samples. Okay. Now what's the sample? What's the bit depth? It's 32. 32 bits per sample for the stereo recordings. 32 is a big number, right? 32 bits. You can represent an amplitude of 2 to the 32. Minus 1. That's a big number. That's pretty amazing, right? Now, recently, the music CD was replaced with MP3. Okay. Now, what the MP3 actually used? MP3 basically used the same number of samples, but the bit depth is actually 16. It's only half of 32. Okay. So now compare with the music CD, the MP3 player. If you want to play a music, most of the time it's going to be the same quality as the music CD. But if the music actually, if you want to play a very loud music, okay, then you probably still need a music CD, because for MP3, if it's loud enough that the amplitude cannot represent it with 16, then you're gonna you're going to have a loss of sound quality, okay, in that case. So that's basically what the digital audio format actually plays. These are very popular two actual music actual format, okay, the music CD and the MP3. So every time when you copy the music CD, copy the data from the music CD to MP, save as MP3, so then you're going to lose some of the quality. Not much, okay, but you're going to lose some of the quality. Now, what do you gain? The space,
You can
right?
store
The
more
file
songs.
size. Okay, the file size is smaller. Okay. Now we can actually take a look at this another example. Okay. Let's say if you want to play a music CD with 3 minutes, to play 3 minutes of music with music CD. How much space do we need to store it? Can you figure out how much space do we need to store a music of 3 minutes in a music CD format? Think about this. Okay, let's take a small break, a very small break, 5 minutes. I'm gonna actually cut the recording because